In this video, we're going to be continuing our lesson about Le Chatelier's principle. We've talked about what it means for a system to be at equilibrium. Today, we're going to talk about how equilibrium can shift in response to the stress of changing the concentration of products or reactants. Our learning goals for this video are: given a chemical reaction equation, use Le Chatelier's principle to predict whether a change in reactant or product concentration will favor the forward or the reverse reaction. Then we will similarly predict whether a change in reactant or product concentration will then lead to an overall increase or decrease in the concentration of reactants or products as the system reestablishes equilibrium. This topic can be a little confusing and counterintuitive, so you might want to watch this video twice. I also suggest taking notes to help you process as you watch, whether you do sketch notes, take them visually, or you kind of write down the text that I have on the screen. First, we're going to do a quick recap about the definition of a chemical system at equilibrium. Now, this can be either a chemical change, like a chemical reaction, or more of like a physical system, like chemicals dissolving in water. Both types of systems can be at equilibrium. So when a reversible chemical system is at equilibrium, when reactants are becoming products, A is becoming B, equilibrium occurs when the rate of the forward reaction is the same as the rate of the reverse reaction. Another way to say this is the forward and the reverse reactions are occurring at the same speed, or that A is turning back into B at the same rate that B is turning back into A. This means that the concentration of A and the concentration of B remain constant at equilibrium. Now, it does not mean that there's the same amount or the same concentration of A as there is of B. It simply means that the amounts of both reactants and products are stable, are constant, are overall unchanging, even as both the forward and the reverse reaction are occurring. Make sure you've seen my previous video talking about equilibrium to really make sure you understand that concept. We're going to look at 4 different scenarios in a system at equilibrium. The example reaction we are looking at is 2HI decomposing to form H2 plus I2. And the reverse reaction is H2 plus I2 reacting to form HI in a synthesis reaction. So this is a decomposition synthesis reversible reaction system. Now let's think about each of the columns of this table here. So when I say stress, what I really mean is the change that is going to occur and be applied to this closed system at equilibrium. When I'm asking which reaction, forward or reverse, will this stress favor, I'm basically saying which reaction will this change, the stress, suddenly cause to happen at a faster rate, the forward or the reverse. When I'm asking about the impact on the concentration of the reactant or the reactants, I'm asking that from the moment after the stress occurs. So for example, the stress is addition of reactant in the first row. I am not going to say that this will increase the concentration of reactants because that column is talking about from the moment after that increase occurs. I'll go over an example in a moment. And then the same thing goes for impact on concentration of products. It's the impact on the concentration right after the stress is applied. So let's think about the stress of adding reactant to the system. So in this case, our reactant is HI. Let's imagine this is the system at equilibrium. We've got forward reaction and reverse reaction occurring at the same rate. If we add additional reactant particles, so if I add more HI to the system, I want to think about which reaction, forward or reverse, is going to be impacted by this change. And then I want to think about, based on how that impact occurs, which reaction, forward or reverse, will be occurring faster, will be being favored as a result of this change. So if I add more reactant particles, obviously the first change that occurs is that I've added more reactant. I've just increased the concentration of reactant particles. But if I want to think about how that's actually going to impact the equilibrium system, I need to think about which reaction this is impacting. So adding more reactant particles is impacting the number of collisions that can occur between reactant particles. More reactant particles means more collisions can occur. We know that as we increase the concentration of reactants, we increase the rate of a reaction. And so increasing reactant particles will increase the rate of the forward reaction, of reactant colliding, reacting and becoming products. So this particular example is favoring the forward reaction. We can notate that by putting the arrows with the forward reaction arrow being a little bit bigger, the reverse reaction being a little bit smaller, because by increasing reactant concentration, we've caused there to be more possible collisions between reactant particles. So the forward reaction is being favored compared to the reverse reaction. Going back to our summary table, if I'm favoring the forward reaction, that means that from the moment that the stress is applied, I am using up reactant faster than I am making product because I added some more reactant and that caused the forward reaction, reactant turning into product, to be favored. This means, and this sounds strange at first because the stress that we applied was adding reactant, but overall, once that added reactant causes the forward reaction to occur faster, the impact on the concentration of reactant particles is actually that they will decrease because the forward reaction is going to be using up reactant faster than the reverse reaction is replacing that used up reactant. So as the concentration of my reactants decreases, the concentration of the products will increase until equilibrium is reestablished. This is an example of a shift to the right. The forward reaction is being favored, shifting to the right. Let's think about what would happen if we added product. So in this case, that could be either H2 or I2 or a little bit of both. We can add either of the products and it would have the same impact. So if I added some product, I want to have the same thought process as I had before. Which reaction, forward or reverse, is going to be impacted? So adding product particles is actually going to impact the reverse reaction because the product particles need to collide with each other in order to react and become reactants again, right? The reverse reaction is products becoming reactants, H2 plus I2 becoming HI. So by adding more product particles, I'm increasing the number of collisions that the products are having. This actually is going to increase the rate of the reverse reaction, while it does not change the rate of the forward reaction. So this change, adding product, will favor the reverse reaction by allowing there to be more product that can turn into reactant. Looking back at our summary table, if the reverse reaction is favored, that means that product is becoming reactant faster than reactant is becoming product. So if reactant is being made faster than product is being made, the concentration of reactant will increase as a result of this equilibrium shift, and the concentration of product will decrease. So this is a shift to the left because the reverse reaction is being favored by this change. Let's think about the opposite scenario. What if instead of adding, we remove? So let's think about removing reactant. So if we get rid of some of the HI particles. So if I remove reactant, I am going to be affecting my forward reaction. By removing reactant, I am decreasing the number of reactant particles present, and this will decrease the number of collisions that reactant particles can have, which will decrease the rate of the forward reaction. So the rate of the forward reaction will decrease. I'm not changing the rate of my reverse reaction by removing reactant, because I haven't changed how many product particles there are. So the reverse reaction, because it hasn't changed, will be favored because I have slowed down the forward reaction, and so this change has favored the reverse reaction. You might want to rewind 30 seconds and rewatch this part again. Looking back at our summary table, if the reverse reaction is being favored because I have slowed down the forward reaction but left the reverse reaction the same, that means that product is turning into reactant faster than reactant is turning into product. So the concentration of my reactant, I'm going to let you guess before I reveal the answer here, the concentration of the reactant will increase while the concentration of the product will decrease as equilibrium shifts to reestablish after that stress. Final example here, I want you to take a look and think about what we've just done and try to fill out that row on your own. Pause the video if you haven't had a chance yet. We're going to go ahead and think about what would happen if we remove some of our products. So if we remove either H2 or I2. So let's say we're starting with this amount. Which reaction will be impacted if we remove product? So if I remove product particles, removing product will decrease the number of product particles present, which will decrease the number of collisions that the product particles can have, which is going to decrease the rate of the reverse reaction. So the rate of the reverse reaction will decrease. This will not change the rate of the forward reaction. The rate of the forward reaction will stay the same. So the forward reaction is being favored by this stress because the reverse reaction is being slowed down, which means the forward reaction is now going faster. It's being favored. If we go back to our table, that means that if the forward reaction is being favored, we are using up reactant and making more product, which means that we are going to decrease the concentration of reactant in the system as the reaction equilibrium system shifts back to equilibrium. And we are going to increase the concentration of product. This is a lot. I recommend rewatching that segment of the video where I went through the summary table, writing the summary table down, and really thinking through what I just talked about. Because you could certainly just memorize that summary table of what happens with each stress, but this will go a lot better for you if you can think to understand each step along the way. We've done a lot of work this video, but let's just do one practice problem to see what these could be like. So given the equation representing a solution equilibrium, so this is an equilibrium of a salt dissolving and coming out of solution and precipitating. What occurs when Na2SO4, sodium sulfate, is added to this system, increasing the concentration of SO4 2-. Now, stay calm here, right? I see a lot in this question about shifting equilibrium. So just a quick note, look at the way that the arrows are pointing. If the forward reaction is favored, that's a shift to the right. If the reverse reaction is favored, that's a shift to the left. Now, if the question is telling me the concentration of SO4 2- is what is being impacted, because the question explicitly tells me it's increasing the concentration of SO4 2-. That is a product in this equation. So if I am increasing the amount of product, that means I am increasing the rate of the reverse reaction because I'm increasing the amount of product particles that can collide, which is increasing the rate of the reverse reaction. This in turn is favoring the reverse reaction in a leftward shift and is actually going to decrease the concentration or the amount of the product because reverse reaction uses up product faster than the forward reaction will make product because the reverse reaction is being favored over the forward reaction. So my answer is number 1. These are tricky problems because they are several steps and it's really easy to get confused. If you're still having trouble after watching this video, we are going to do more equilibrium practice in the next 2 videos as well. Great job today.